the next problem, which is essentially the same. It adds one particular constraint. So you're given the same prices array. You can complete as many transactions as you like. You can't obviously buy multiple stocks at the same time. You can only hold one stock at a time. Uh, so that's this constraint. The new thing that this problem adds is that when you sell your stock, you cannot buy the stock either on the same day or even on the next day. Right? So you have to leave at least a 2-day gap between a sell event and a subsequent buy event. So in this particular toy example, well, firstly, this is quite straightforward because there's only one index. So there can't be any transactions anyway, so there won't be any profit. In this toy example, if there were no restrictions, if we were in the previous problem, then we would have bought low here, we would have captured this gain, we would have sold at a price of 3 and then bought immediately at price 0 and then captured the gain from 0 to 2. So it would have been 3 plus 2, which would be 5. Now, because of the constraints of this problem, we can't buy the stock at a price of 0 because we just sold it on the previous day at a price of 3. So we have to wait for at least 2 days. So the optimal solution here is actually to buy at a price of 1, but instead of waiting till it climbs to 3, sell it 1 day before, even though the profit here is just 1. But by waiting for 2 days, we get to buy it again, and this time the profit is 2. And so the total would be a profit of 3. Whereas there would only be a profit of 2 if we had bought and sold here and then being unable to buy here. So that would have been 3 minus 1, which is 2. So so we have to handle this constraint. That's the problem. So let me just give you a minute to think and then we'll follow the same approach. Okay, so let's follow the same approach. We'll have decrease and conquer approach where we take the global problem and uh, create a generalized subproblem out of it, which applies to an arbitrary manager in the hierarchy. So let's actually keep the definition the same. G of I would be maximum profit with any number of transactions up to index I. The maximum profit with any number of transactions up to index I. So if I am a lazy manager, a general lazy manager, I am given an array which, as far as I'm concerned, ends at index I. I'm assuming that someone before me has solved the problem up to index I minus 1. So I'm asking, how can I extend that solution up to index I? So that really depends on what happened on day I. So we'll do the same thing. Let's say on day I, what could have happened is, well, option 1 is nothing. Nothing happened on day I. In which case, the global solution for my problem would be the same as the global solution computed by my subordinate for his or her subproblem. And if something did happen on day I, if there was a transaction, could have been a sell transaction. And so if we ask what was the purchase date for that sell transaction, we'll divide it into two categories again, previous day, and group together the earlier days with the hope that we can just collapse all those cases into some optimal case for our subordinate, which we will just use and extend. So if the purchase date was the previous day, then the maximum profit that I would accrue to day I would be uh, the profit from the last transaction, the final transaction, which would be the delta in the price, right? This was the last transaction. And then we would say, up to index I minus 1, what is the maximum profit that could have been accrued? But because this transaction started at day I minus 1, we are assuming that we bought it on day I minus 1. If we look back to whatever is the best solution up to that point, that best solution could not have had a transaction ending on day I minus 1 or even on day I minus 2 for that matter, because there has to be this minimal cooldown period. So previous to index I minus 1, uh, there could have been a sell up to index I minus 3, right? We need at least a 2-day gap between a sell event and the next buy event. So if the buy event happened on day I minus 1, any prior transaction to it would have ended at index I minus 3. So what we would want to information on is, what is the solution to the subproblem ending at index I minus 3. So we take that solution and we add the price of this last transaction to it, and that gives us the maximum profit up to day I, assuming that the last transaction happened on the on the last 2 days. So we will add to this a g value, but not so if we go back to what we did without having any constraints, we had a g value at index I minus 1, right? We were looking at any number of transactions that end at day I minus 1 and take the profit from those. Now this changes to I minus 3. And if the purchase happened on some earlier day. So what's the best possible transaction from an earlier day that can end on my day? Well, any best possible transaction here by the same argument would have a prefix that's also a best possible transaction ending on day I minus 1. So in other words, this prefix, which is one shorter, would also be the best possible transaction uh, under the given constraints that ends with a cell on day I minus 1. That's the transaction that I want to extend, because if the green transaction was not the best transaction, I could replace it with the best transaction and extend that and get a better transaction. So uh, so what I want, if I want to use my subordinate solution, is what's the maximum profit? The maximum profit with any number of transactions ending at index or day I minus 1 with a cell I'll cover this in blue again. So this is not the same subproblem with a smaller size. It's a different subproblem. So it is what we will call as F. Of course, to this is what we are extending. So when we extend it, we will need to add the delta in the price. So here, by the way, we are not just comparing when we say that the green prefix can be replaced with a better solution, if there was a better solution, that better solution, if there was one, is not necessary, it wouldn't have been better as far as a single transaction is concerned, right? We are looking at the entire history here. It would have been better as far as the entire history was concerned. Maybe that last transaction could have been worse off, but as long as the entire history was better, we could take that better solution, replace what we see here with that, a bunch of transactions here with some final transaction, and then extend that final transaction, which has to end at index I minus 1. That's the constraint. It has to end at index I minus 1 with a cell. The best such history is what we are extending. Same thing for the previous problem. So this is what we'll call as f of I minus 1. F of I, the maximum profit with any number of transactions up to index I with a cell happening on day I. So again, let's write the equation for g of I, and then we'll write an equation for f of I. So g of I is going to be the max of those three values again, max of g of I minus 1, comma, uh, the other two will be the delta in the price plus g of I minus 3, and the delta in the price plus f of I minus 1. So I hope I don't need to go through those intermediate steps. I could just write it as the delta in the price plus whichever is bigger among these two, g of I minus 3 and f of I minus 1. So the delta in the price plus whichever is bigger between g of I minus 1 and, let's see, what was it? Sorry, g of I minus 3 and f of I minus 1. So that's the expression for g. What's the expression for f? Um, so f of I is the maximum profit with any number of transactions up to index I, necessarily with a sell happening on day I. So if there is a sell that has to happen on day I, the question is, when did the buy happen? Right, and to figure out when the buy happened, we could basically look at the same diagram and say either the buy happened on the previous day, in which case we would look at uh, the price of that transaction and then add to that the the best solution up to index I minus 3, because there is this cool down period, or that buy happened on some earlier day, in which case we will rely on our subordinate to tell us what's the best solution that ends with a sell on index on day I minus 1, and we'll just take that and extend it by adding the delta. So in effect, this entire thing is just f of I, right? Because g of I is either nothing happens or there is a sell that happens on day I, and whenever there is a sell that happens on day I, that the definition of the subproblem that we are looking at is f. So it's not surprising that for all these problems, g of I is basically the max of g of I minus 1 and f of I. But if you didn't notice it, even if you wrote it from scratch, you would see that it's the same definition, that either that transaction happened on the previous day, in which case we would need to add this also, or we are extending it from the from our subordinate's solution, in which case we have to add f of I minus 1. So it's going to be the max of g of I minus 3, f of I minus 1. So this basically is the same as this, and so we can write the two recurrences as f of I is the delta in the price plus max of these two, and g of I is the max of g of I minus 1 and f of I. This is what needs to be translated into code. So we again have as our base cases, if there was only one day, right, f of 0 is going to be 0, g of 0 is going to be 0 as before. Now there is this I minus 3 term here. So technically we need three base cases. So we have a base case for 0. We also need to figure out what the values of f and g will be. Sorry, values of f and g will be uh, if I was 1 and if I was 2. If we have that, then 3 onwards we can use these two recurrences. But if you think about what the value could have been on days 1 and 2, the g values won't be any different. G values would just be whatever can be done from the previous day and any new thing that happens with the sell event on the new day. So we have to think about f of 1 and f of 2. Both f of 1 and f of 2 are extending the uh, well, we assume that the last the delta, the final delta from I minus 1 to I is already there in our transaction since we have to sell on day I. Uh, Now, whether the when did the buy happen? That is what's uncertain. If the buy happened on the previous day, this would be the price. Otherwise, the price would be uh, extended with whatever happened. Uh, whatever was the best solution before. This does not exist if I is 1 or 2. Right? There is no competitor here uh, because any buy that happened when I is 1 or 2 could not have been preceded with another transaction. So there are two ways to go about this. One is to write what f of 1 would be uh, and what f of 2 would be. And in fact, you can, if you want to think about what it should be intuitively, you would guess that, if it would be a single transaction that ends at 1 or ends at 2 and captures as much profit as possible. So that means uh, if whatever prior lowest price there is, we'll pick that as the buy date and uh, sell it on day I. So that's one way to do it. The other way is to just say that I will ignore this term if I is less than 3. Right, so let's go with the latter approach. If I minus 3 is less than 0, ignore g of I minus 3. Because there is no global history prior that we need to worry about. We just have to look at the uh, whatever our subordinate came up with and extend that, or we begin a fresh transaction here without worrying about the global history. Right, these are the only two options. If I start a new transaction from the previous day, I don't worry about the global history. But if I'm extending the transaction, then yes, I take that and add the delta. So with this small change, nothing else really will change. We write the code using same uh, structure, one-dimensional array of size n, initialized to 0. F table would be the same. F of 0 and g of 0 are both 0. So they are 0 by default from our initialization. Then we'll have a loop that goes through 1 to n minus 1, and we just calculate f of I, store it in f table of I, calculate g of I, store it in g table of I. So f of I is the delta in the price, f table of I will be the delta in the price plus the max of g of I minus 3 and f of I minus 1. I'm not writing it as g of I minus 3. I'm saying get g of I minus 3 just because, we'll, if I is less than 3, then we just want this to be 0. So why not just have a, function that will, uh, when we ask it to return a g value at any index, it will just return a 0 if the argument is less than 0. Otherwise, it will just return uh, whatever the value is in the G table at that index. So here I should write F table because stored in index I minus 1. And then the G table value will just be, as usual, the older value, and comparing that with the new F table value. Finally, return G table of n minus 1 as always. If we compare it with the previous problem was actually turned out to be even more simple when we the problem was not simple, but the code turned out to be even more simpler uh, when we saw that G is always more than F and all. But even if you don't see that, even if you write it with the same structure, I think it'll be fine because this is not the greedy algorithm path. This is plain decrease and conquer path, and so to get that same code, you need those additional optimizations which are not mandatory. So the time complexity is going to be order n because the body of the for loop again runs in constant time. The auxiliary space used was order n, but because we rely on only a history of length 3, so let's say we only keep the last 3 or 4 values, we can bring it down, can be brought down to constant time, sorry, constant space. Okay, see if you have questions. Manish?
Hi, Omkar. Can you hear me?
Yeah, yes.
Yeah. So, can you please go to that diagram previous day and earlier day?
This one?
No, the other
Or
one.
the diagram, okay.
Diagram, yes. So here in earlier day, we are doing sale at index I minus 1, and we have a cooldown of 1 day. And I did not get this part, how we are adding the delta over here again. Because
On the earlier day or previous day?
so earlier day.
Earlier day.
Yeah.
So in the earlier day, we don't worry about the cooldown because we are not starting a transaction. Here, we are kind of we are seeing the whole transaction, right? This transaction starts at I minus 1 and ends at I.
Yeah.
And so the history prior to that has to be seen by us, keeping in mind the cooldown period.
Yeah.
Because the transaction starts on day I minus 1. Here, the transaction started on some earlier day, and so it falls the start date of that transaction falls, goes behind that fog, that within that red rectangle. And so I don't have to worry about it because I'm just looking at the last transaction now and extending that. It's my subordinate or subordinate of my subordinate. Somebody there had to, worry about uh, the cooldown, and they would have done it by using the same method that I used if I was beginning a transaction, or if I was like, uh, yeah, if I was looking at a transaction that starts from the previous day. Somebody within that red rectangle would have also seen a transaction start on the previous day for the longer transaction that I'm seeing up, at my index.
So actually, I got confused because that we have a statement here, max profit with any transaction at index I minus 1, and we are adding delta at index I, taking the previous purchase. Uh,
Yeah,
That's it.
because what we want is the maximum profit. So we want to extrapolate this to day I. That is why we are adding this.
Yeah.
So from our purposes on day I, what happens if there is a transaction, then we want to make sure that we maximize the profit up to index I,
Mhm.
uh, keeping in mind that transaction. If that transaction started was very short, then we do it this way. But if it was long, then we actually use our subordinates uh, solution for f and extend that, and then we pick whichever is the bigger among these two.
Okay, so we are extending solution. That's why we are doing this.
Yeah, we didn't begin any new transaction, or
Mhm.
we didn't have any cooldown period or anything in the middle.
Mhm. Okay, got it. Yeah, thank you.
Okay, so if there are no more questions.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today